Imagine for a moment that you're back in your school science lab. You have a simple battery, a small torch bulb.
Okay.
You cut the connecting wires. Now, if you touch those cut ends together, of course, the bulb glows. Simple circuit, right?
And a closed circuit.
Now, imagine you dip those two separate wire ends into a beaker of salt water. The bulb. It glows brightly. It's almost as if the water is a wire.
That is a classic experiment, yes.
But wait, here's the mystery. If you take that same setup and dip the wires into a beaker of sugar water, which looks exactly the same, just a clear, transparent liquid, the bulb stays completely dark.
Nothing.
Nothing happens. Why is that? I mean, why does common salt act like a bridge for electricity, but sugar acts like a complete roadblock?
That is the fundamental question. And it's not just about what we can see. It's really about the invisible traffic system that's operating inside those liquids.
And that is exactly what we were unpacking today. Welcome back to the Deep Dive. Today we're tackling conductance of electrolytic solutions. This is a core topic from Unit 2, electrochemistry.
Ah, a very important one.
If you're a Class 12 student listening to this is definitely going to be on your board exam.
Absolutely. And even if you're not a student, I think understanding this is just fascinating. It explains how we move energy through liquids.
Before we get into the technical details, tell us, why should we care about this? Beyond just exam marks, does this concept matter in real life?
Oh, it matters immensely. Think about it. This concept is the key to understanding how ions move to create current. Without understanding conductance, we couldn't predict how fast electrolysis happens in factories.
Like what kind of factories?
Well, we wouldn't be able to refine metals like copper, and we certainly wouldn't be able to check if our drinking water is safe using those little digital testers.
That's a big claim, from factories to our drinking water. So let's start at the very beginning. At the simplest level, the zero-level explanation.
Right.
What are we actually talking about when we use this word conductance?
At its simplest, conductance is just the ability of a solution to conduct electricity. It's a measure of how easily current can flow through it. But, and this is a huge but, we must be very careful, there's a huge difference between how, say, a copper wire conducts electricity and how a glass of salt water does it.
Right, let's clarify that distinction immediately. In a copper wire, like the ones in our house walls, it's the electrons doing all the moving, correct?
Correct. In metallic conductors, you have this lattice of metal atoms that they stay put, and a sea of electrons just zips through them. The current is carried by electrons.
But in a solution, say in our beaker of salt water, can electrons just swim through the water?
No, absolutely not. Electrons can't swim. They can just jump off the wire and paddle across. In an electrolytic solution, the charge is carried by ions.
Ions.
Yes. These are charged particles, atoms, or molecules that have either lost or gained electrons.
So in the wire, the vehicle is the electron, but in the water, the vehicle is the ion.
Exactly. And to really understand this, I want you to visualize it. Maybe close your eyes for a second. Imagine a massive, crowded wedding hall, or a large room just packed with people.
Okay, I'm picturing a very, very crowded room.
Good.
Yeah.
These people represent the ions in the solution. Let's say we have dissolved sodium chloride. So you have positive people, the sodium ions, and negative people, the chloride ions.
Okay.
Now, normally, they're just wandering around randomly, bumping into each other. That's just thermal motion.
No, it's the chaos in there.
Total chaos.
Yeah.
Now, imagine we apply an electric field. This is like putting a loudspeaker on one wall that shouts, all positive people come to this side. And another loudspeaker on the opposite wall that shouts, all negative people go over there.
So the crowd starts to split up.
Yes. The positive people, the cations, start rushing towards the negative side, which we call the cathode. And the negative people, the anions, start rushing towards the positive side, the anode.
I see.
This coordinated movement, this drift of the crowd in opposite directions, that is the electrical current.
That is a brilliant mental image. So unlike in the wire, where the atoms are standing still, in the solution, the particles themselves are physically moving across the entire room.
Precisely. And this leads us to our anchor definition. If you're writing an exam, you should note this down. Conductance is the ability of a solution to conduct electricity.
Okay.
And critically, it depends on two things. The concentration of ions, meaning how many people are in the room, and their mobility, meaning how fast can they run.
Concentration and mobility. That seems straightforward enough. But I'm looking at our notes here, and there's a big red warning label. It says misunderstanding trigger.
Yes. This is where I would say 90% of students lose marks. You must not, under any circumstances, confuse conductance with conductivity.
They sound almost identical.
Mm-hmm.
Conductance, conductivity. I mean, in normal English, they're basically synonyms, but in chemistry, they're different.
Oh, they are very, very different. Mixing them up is like confusing the weight of a gold bar with the density of gold.
Okay, please break that down for us. This sounds important.
Let's start with conductance, which we represent with a capital letter G. Conductance is a property of the specific sample you are holding. It depends on the size of the container, the amount of liquid, and the geometry of the electrodes.
So if I have a tiny cup of salt water versus a giant swimming pool of the exact same salt water,
Yeah.
their conductance is different.
Yes, completely. Because the swimming pool has a much wider path for the ions to move through, it creates less resistance. So conductance is an extensive property. It depends on quantity and dimensions.
Okay, then what is conductivity?
Conductivity, represented by the Greek letter kappa, is an intensive property. It is a constant for the solution itself. It doesn't care if you have a drop or a bucket. It defines how well that specific chemical mixture conducts electricity per unit area and per unit length.
I think we need an analogy here. The ballroom was good for movement, but for this geometry stuff, let's maybe use the traffic on a highway analogy.
That is the best way to understand it, I think. Imagine the solution is a highway connecting two cities.
Okay, I'm visualizing a road.
Now, conductance G is like asking, how many cars can get from city A to city B in 1 hour on this specific road?
Well, that would depend on the road, no. If I build a super wide 10-lane highway, more cars can pass through.
Exactly. A wider road allows more flow. In our chemistry lab, a wider road means electrodes with a larger area, A. Larger area means higher conductance.
And what if the road is very, very long?
If the road is very long, it just takes more time to get across. The flow is restricted. In the lab, a long road means the distance between the electrodes, L, is large. So conductance decreases as the distance increases.
So conductance G is totally dependent on the dimensions of the road, its width and its length.
Correct. Now think about conductivity. Conductivity is like the speed limit of that highway.
Ah, I see where you're going with this.
It doesn't matter if the road is 5 kilometers long or 500 kilometers long. If the speed limit is 100 kilometers per hour, that's a rule of the road. It is a property of the traffic system itself.
So even if I have a narrow road, if the speed limit or the intrinsic ability of the cars to move is high, that means it has high conductivity.
Exactly. Conductivity is the intrinsic flowiness of the solution. To be scientifically precise, conductivity, CANI, is defined as the conductance of a solution, specifically when it's kept between electrodes that are 1 centimeter apart and have a cross-sectional area of 1 square centimeter.
So it's like we're taking a standardized 1-by-1 chunk of the highway to judge the traffic condition.
Perfect. That is exactly it. You've got it.
There's another analogy I've heard sometimes, the water pipe analogy. Does that work here as well?
It works very well as a backup mental image. Think of conductance as the amount of water coming out of a pipe. A thick, short pipe gives you a lot of water high conductance.
Right.
A thin, long cocktail straw gives you very little water low conductance.
But the water inside.
The water inside is the same. Its intrinsic fluidity, its viscosity, that's the conductivity. The pipe dimensions determine the overall conductance.
That makes it crystal clear. So why does this concept even exist? I mean, why did scientists like Georg Kohlrausch in the 19th century spend so much time figuring this out? Was it just for fun?
No, it solved a major problem. You have to remember, back then, they couldn't see molecules. They needed a way to quantify ion movement. Kohlrausch used this to understand dissociation.
Dissociation.
What's that? Well, he wanted to know, when I dissolve a substance in water, does it break apart completely into ions, or does it sort of stay stuck together? He realized that by measuring conductivity, he could tell the difference.
Oh.
Strong electrolytes, like salt, they break apart completely. Weak ones, like vinegar, only break apart a little bit.
So conductivity was like a detective tool to see what was happening at the molecular level.
Exactly. And today we use it for designing industrial systems. If you're an engineer designing a plant to produce chlorine gas or to purify copper, you absolutely need to know how conductive your solution is.
Why is that so critical?
Because you need to design the right size tanks and the right power supplies. If you assume the wrong conductivity, you might apply too much voltage and overheat the system.
Oh, that's bad.
Or you apply too little and the reaction barely creates any product. It is a fundamental design parameter.
Okay, I want to cement this in our listeners' minds.
Right.
Let's build a mental movie of the lab setup. I want everyone listening to picture the apparatus.
Okay, let's go into the lab. Picture a glass beaker on a black table.
Got it. What are we pouring in?
Let's pour in a clear solution of sodium chloride NaCl dissolved in water. It looks just like plain water.
Then we need the electronics.
You take 2 platinum electrodes, these are just small metal plates or strips, and you dip them into the liquid. They are fixed at a specific distance from each other.
Okay.
You connect these plates to a battery, and crucially, you connect an ammeter in the circuit.
The ammeter that measures the current flowing. So I'm flipping the switch on the battery. Action.
Now, visualize the invisible. Inside that clear liquid, millions of sodium ions, Naplus, suddenly feel the pull. They start drifting toward the negative electrode. At the same time, the chloride ions, Cl, they drift toward the positive electrode.
And what do we actually see on the table?
The needle on the ammeter jumps up. It shows a high number. That number is the evidence. It proves that the ions are moving.
Now cut. Let's change the scene. Swap the liquid. We pour out the salt water and pour in pure distilled water. Flip the switch again.
The needle on the ammeter just drops. It goes to nearly 0.
Because there are no ions, there are no cars on the highway?
Exactly. The road is open, the battery is pushing, but there are no vehicles to carry the charge.
This actually brings us right back to the examples we touched on in the intro. We talked about the light bulb. Let's go through those scenarios one by one so the students can really categorize them.
Sure. Let's start with tap water.
If I dip the wires in tap water, the bulb usually glows, but it's a bit dim. Why is that? I thought water was an insulator.
Pure water is an insulator, but tap water is not pure. It has dissolved minerals, calcium, magnesium, maybe some chlorides from the treatment plant. These are all ions.
Oh.
They're not very concentrated, but there are enough of them to carry a weak current, so you get a dim glow.
Okay. Then we have distilled water.
Distilled water has had all those minerals removed, so no ions. The bulb is off.
Then we add salt and NaCl.
NaCl is what we call a strong electrolyte. It dissociates completely. Every single molecule breaks into ions. Suddenly, you have a massive traffic jam of charge carriers moving freely. The bulb glows very brightly.
And what about something like vinegar?
Vinegar is acetic acid. This is a weak electrolyte. It dissolves, yes, but only a small fraction of the molecules actually break apart into ions. Most of them stay together as neutral molecules.
So you just have fewer cars on the road.
Far fewer. So the bulb glows, but dimly.
And finally, the sugar solution from our hook at the start.
Sugar is a non-electrolyte. When sugar dissolves, the molecules separate from each other, but the sugar molecule itself doesn't break. It stays as a neutral particle.
No charge.
No charge means the electric field has no effect on it. It just floats there, so the bulb stays completely dark.
That is such a clear way to distinguish between them. Now, is there a specific piece of technology that uses this principle? We mentioned water testing earlier.
Yes. Have you ever seen a TDS meter? The water purifier service technicians, they usually carry one. It looks like a thick digital thermometer.
Yes, I have. They dip it in a glass of water and it shows a number, like 150 or 300.
That device is actually a conductivity meter. It applies a small voltage to the water between 2 tiny pins. It measures the current. Then it uses Ohm's law, V equals IR, to calculate the resistance. And from that, the conductance.
And then it just converts that to a number for us.
Yes, it converts the conductance into ppm, or parts per million of total dissolved solids. Basically, it assumes that higher conductance means more dissolved salts and minerals.
So it's essentially just counting the ions to tell us how pure our water is.
Exactly. A high reading means lots of ions, so maybe hard water or salty water. A low reading means fewer ions.
That is very cool. It's a practical application of Class 12 chemistry right in our kitchen. Now, I want to bring up a counterintuitive example from the notes. It says something here about a traffic jam.
Yes. This is a nuance that often catches students out. You might think, okay, if salt adds ions, then adding more and more salt should always increase the conductance linearly. Double the salt, double the current.
It sounds logical. More cars, more flow.
But actually, at very high concentrations, the conductance might not increase as much as you expect. It might even start to flatten out.
Why? What happens?
Well, think about that crowded room on the highway again. If you pack too many cars onto the road, bumper to bumper, can they move fast?
No, they would slow down. It becomes a jam.
Exactly. The viscosity of the solution effectively increases. The ions start bumping into each other more. Also, positive ions might get surrounded by so many negative ions that they actually get pulled back. This reduces their mobility.
So even though you have more cars or ions, they are moving much slower because of the overcrowding.
Precisely. So conductance depends on concentration, yes, but we must not forget mobility. And at very high concentrations, that mobility drops.
That is a great point for the conceptual questions. Okay, we have covered a lot. For the students listening, we need to ensure they have the exact keywords for the exam. Let us do our exam-safe clarity lines. I'll say the category, you give us the key takeaway.
Let's do it.
Point 1, the units.
Conductance G is measured in Siemens, which is a capital S. Conductivity is measured in Siemens per meter, SC, or Siemens per centimeter, SCM. Don't mix the units up.
Point 2, the direction of flow.
In electrolytic solutions, current is carried by ions moving in opposite directions. Cations move to the cathode, anions move to the anode. This is completely unlike metals, where electrons move only one way.
Point 3, the factors affecting conductance.
Conductance increases with ion concentration, the number of ions, and ion mobility, how fast they move. Also, temperature plays a big role.
Oh, how does temperature affect it?
Unlike metals, where resistance increases with heat in solutions, conductance actually increases as the temperature goes up.
Why is that?
Because as you heat the solution, the viscosity decreases, the water gets thinner and runnier, so the ions can move faster through it.
Got it. Point 4, strong versus weak.
Strong electrolytes like NaCl or HCl dissociate completely and have high conductivity. Weak electrolytes like acetic acid or ammonium hydroxide dissociate only partially and have low conductivity.
And finally, point 5, the big one.
Remember that conductance, G, is an extensive property. It depends on the sample size, while conductivity, Co, is an intensive property, independent of sample size.
You had a mnemonic for this earlier, didn't you?
G, so forgiven. Conductance is for the given sample geometry. Kappa is the constant property of the material.
G is given, kappa is constant. Hope everyone wrote that down.
It saves lives in the exam hall, really.
Let us wrap this up with a short summary. If you had to summarize this entire deep dive in, say, 3 sentences, how would you do it?
Sentence 1. Conductance in solutions is the flow of current carried by ions, not by electrons.
Okay.
Sentence 2. Think of the highway analogy. Conductance depends on the road dimensions, the geometry, while conductivity is the intrinsic speed limit.
Perfect.
And sentence 3. Strong electrolytes light the bulb brightly because they provide plenty of ions, while weak electrolytes will leave it dim.
That perfectly sums it up. Before we sign off, leave us with one final thought about why this matters in the big picture. We talked about water testing, but is there anything else?
Think about the chrome plating on a car bumper or the gold plating on a cheap watch. That is all done by electroplating. It's a massive industry. And when they are plating that metal, they're relying entirely on the conductance of the solution. If the conductance isn't just right, maybe the concentration is off or the temperature is too low, the current won't flow correctly. You might get a patchy coating or a burnt coating, or it might just peel off.
Oh.
Conductance is basically the volume knob that engineers use to control these massive chemical reactions.
I love that. It's the volume knob of the chemical industry.
It really is.
Well, there you have it. From the salt in your soup to the gold on your watch, it is all about the traffic flow of ions. Thank you so much for guiding us through this invisible highway.
It was my pleasure. Keep learning.
And to our listener, next time you see a light bulb or drink a glass of water, remember the chaos happening at the atomic level. You are now ready to tackle this topic in your exams. See you in the next deep dive.